Hello and welcome to the 17th lecture in this series, and in this lecture I am going to show that the tangent space of an n-dimensional manifold is a vector space of dimension n. So let me begin by recalling what we have been doing in the last few lectures. So we started by discussing the case of the manifold being Rn itself. So, and in this case we showed that the tangent space at any point of Rn can be identified. In other words, identified, i.e., there is a linear isomorphism with, so let me put this linear isomorphism with Rn. Here, so in this first statement we showed that the tangent space, when I say this, we are working with, so let me call that 0, tangent space at a point P. At point P we define to be the space of derivations of C infinity m at P. Well, in this so that's, and then with this definition in hand, so tangent space, with this definition in hand, we showed that the tangent space, when the manifold is Rn, the tangent space can be identified with Rn. And in the last class I talked about the differential or derivative of a smooth map f from m to n. This turned out to be a linear map dfp at P in M. Df tangent space to M at P, tangent space to f of P at N. And the definition was as follows. So dfp, so let V belong to TPM. I want to see what dfp of V is. dfp of V is supposed to be an element of TFP of N. In other words, it's a derivation on C infinity N, which based at P. So in order to say what dfp of V is, I have to act it on the function phi, where phi belongs to C infinity N. And this is supposed to give me a number, dfp of V acting on phi. And this we define to be V acting on phi composed with f. Phi composed with f will turn out to be a C infinity function on M. And then I can act V on that and get a number. So this was our definition of derivative. And to make sense of this, one doesn't really need to know that what the dimension of these TPM is and so on. In fact, we showed that we have the chain rule. For derivatives. This was towards the end of the last class, and along with that I also showed that the derivative of the identity map is the identity linear map on tangent spaces. So with all this in hand, now we can try to work out what the dimension of the tangent space of a manifold is. Well, before I do that, let's observe that, note that note that 3 implies the following. If f from m to n is a diffeomorphism, i.e. a smooth bijective. The definition of a diffeomorphism is the same as what we had for open sets in Rn. And so it's a smooth bijective map such that f inverse from n to m is also smooth. If we have a diffeomorphism, then dfp from tpm to df of pn is a linear isomorphism. And this follows from 3 because after all we have the proof for this statement is that f inverse composed with f, this would be the identity map on M, which I'll denote by I subscript M, and the other way would be f composed with f inverse. That would be the identity map on N. Now property 3 which I wrote above is the chain rule. So let's apply the chain rule to both of these equations, and I'll get the first one will give me df inverse composed with df equals d of identity, which is identity again. But this identity is the identity. So let's see where this maps go. So if I start with P, so I'll have to put identity at P, and here this would be at f of P. What we are working with is f composed with f inverse is after all a map from, so first I have TPM, this will DFP will take me to df of P n, and df inverse at f of P would take me back to TPM. So this identity here is just this identity from this TPM to TPM. So what I have is that, so this tells me that therefore I have DFP and DF inverse at FP. The composition is identity, and if I, so that's what I got from this. And if I work with this, with the second one, if I knew that all these spaces are finite dimensional, just this one equation would be enough, but I have not proved that yet. So I'll use both equations here, this as well as this, and similarly, if I work with the second equation, for working with the second equation, I'll start at t f of p of n. F inverse will take me back to, rather df inverse at f of p will take me back to tp m, and if I apply f now, I'll go back to df of p n. So I have this, and again the chain rule tells me that df at p compose with df inverse at f of p equals the identity map. This time identity map would be the identity map on tf of p n. So if I combine these two equations, so this as well as this, the proof is complete. So the DFP would be a linear isomorphism. Right. So we will need this. That is one observation. The second thing is that also note that if U phi is a chart on M, as usual I have this is M, this is U, phi is a map from here to what I've been calling U1 inside, this is inside Rn. Then phi from U to U1 is a diffeomorphism in the sense that I defined just now. Namely, well, U itself is a manifold, as we saw earlier. An open subset of a manifold can be regarded as a manifold in a very natural way. Namely, the charts for U are essentially the charts for M, but you shrink the size of the open sets just by intersecting with U. The chart maps will be the same. So U itself is a manifold, U1 is a manifold, and what we are saying is that then the chart map is automatically a diffeomorphism. So this is i.e. phi from U to U1. Maybe I should change this slightly. Should make it seem like U. Phi from U to U1 U to U1 is smooth, and phi inverse from U1 to U is also smooth. Smooth and phi inverse. Phi is since the chart is by definition a homeomorphism of U to U1, phi is automatically bijective. What we are worried here, what we are concerned with here is the smoothness of phi. But it is smooth in a very trivial sense, because after all our definition of smooth is that a map is smooth if in suitable charts, after composing with suitable charts, it's smooth. Well, if we are working with the chart map itself, this is because in the chart, so I have to draw the picture slightly schematically in a different way. So now I'll make the map horizontal sort of U1, and this is U. So I'm asserting the smoothness of this phi. So according to our definition of smoothness, I have to find a chart here and a chart here, if I can find a chart here and a chart here so that the composition is smooth. So I'll need a chart here. Let's call it C, and this is alpha. Well, we choose the obvious charts, namely, let's take C equal to phi inverse and alpha equals identity. So I'll end up back in U1. Here I'll end up in U1 as well. So in the charts, U phi inverse, not quite, it's not phi inverse, rather U is phi itself. U phi and U1 identity, we have, so I want to go like this. I want to go in this direction and come here. So I want to check whether this map is smooth here. And that is trivially true because I just get the identity. So we have, so the last map is identity, this map is phi, middle map, and this map is phi inverse. And this is supposed to go from U1 to U1, and this is just identity. So this map is identity. Similarly, one can check that phi inverse. Similarly, phi inverse is smooth. So the fact that chart maps which are to begin with homeomorphisms are diffeomorphisms is just a consequence of the definition of a smooth map. All right, so we have that. Now let me just quickly outline the idea of the statement, proof of the statement that the tangent space of an n-dimensional manifold is a vector space of dimension n. So theorem, let M be a n-manifold and let P belong to M. Then dimension of TPM is n. Idea of proof. So let U phi be a chart around P. So this is P, this is U, the bigger thing is M. So I have a chart map phi to U1, which is in Rn. Now, based on what I said earlier, there are two things. One is that this phi is a diffeomorphism from this manifold U to the manifold U1, and we have also seen that if you have a diffeomorphism, then the derivative of a diffeomorphism at various points will give an isomorphism of tangent spaces. Since phi is a diffeomorphism, between U and U1, d phi P from TPU to T phi of P U1 is an isomorphism. This is what we just observed. But finally, we are interested in TPM rather than TPU. So we want to relate the tangent space TPU to TPM. Similarly, for this U1 as well, I want to relate T phi of P. So phi of P is somewhere here. The tangent space to U1 at phi of P with the tangent space to Rn at phi of P. So what I need is, suppose we know the following. Let U contained in M be an open set and P in U. Then if we denote the inclusion map I by I from U to M, the inclusion map is just I of x equals x for all x and u. If we denote the inclusion map by this I, then the statement is di p from tpu to tpm is an isomorphism. In other words, if you have an open subset of a manifold and a point inside the open subset, then whether you look at the tangent space to the open subset at that point or the full manifold at that point, they are the same. So that's what we are saying here. DIP is an isomorphism. Now I can go back to this picture here and use this both for U and M and U1 and Rn as well. So I have this was M, this was U, and I have a P here and I have phi. This is phi of P. This is in Rn. And I know that the tangent space, this d phi sets up an isomorphism between tangent spaces to U and U1. So, but now knowing this statement here, we have what we want. Finally, so what do we, well, we have two things. One is TPM is isomorphic to TPU by this, what I just stated, this statement here. And since phi is a diffeomorphism, I also know that this is isomorphic to T phi of P of U1. Again, back to this statement, this time I'll apply it to U1 contained in Rn. So I'll get this is isomorphic to T phi of P Rn, and which this, the last one here, is the tangent space to Rn at some point, and this we have already seen is isomorphic to Rn itself, which is isomorphic to Rn. So finally I get that, therefore TPM is isomorphic to Rn. So this is the basically the idea of the proof. Now let me, so in this proof I proved everything except in this idea, the only thing we need to know is this one, that if you have an open subset, then the tangent space at any point to the open subset is the same as the tangent space to the full manifold. So let's prove that. So proposition, let me write that again. If U contained in M is open, then DIP, P belongs to U, DIP from TPU to TPM is an isomorphism where I is the inclusion map. So for this we need a small lemma. So the lemma is the following: let phi1, let phi be a C infinity function on M such that phi of x equal to 0 for all x in some U, where U is in some open subset of M containing P. So this is M, you have a P, and you have some open set, and the hypothesis is that the C infinity function phi from M to R is identically 0 on this open set containing P. Then the claim is that if V is any tangent vector to M, then at P, then V of this map, this function phi is 0. So what we are saying is that even though the function phi may not be 0 on the whole manifold, if it is 0 in a neighborhood of the point P, then if we act a tangent vector thought of as a derivation, then it is V of phi is 0. And this should not be a surprise if one keeps in mind that after all we think of this action of V on phi as essentially taking directional derivative of phi in the direction V. Now if phi is identically 0 in a neighborhood of P, then all derivatives of phi are also 0. Therefore V of phi is 0. And in fact, one can easily make this precise working in local coordinates, but rather let's prove it like this. So what I'll do is, I'm already given an open set U and a point P inside that. So I'll take another, let me take a chart around the point P. Let U tilde and then alpha be a chart around P by considering U tilde intersection U. After all, you already had an open set U, but the chart may not lie inside U, but that's not a problem. By considering this intersection, we can assume that the chart u tilde is actually contained in u. Let f be a C infinity function on M with support contained in u tilde and f of p equal to 1. So I'll show in my next lecture how to get such a C infinity function. This essentially follows from the discussion that we had about the existence of C infinity functions in compact support in Rn. Now consider f times this original function phi. Let's call this g. This is a product of two functions, f times phi. Well, inside u tilde, if x is inside u tilde, then g of x equal to f of x times phi of x is 0 simply because since this original function phi is identically 0 on u tilde, actually it's 0 on u. So it's 0, and if x is in the complement of u tilde, so let me put it like this, m minus u tilde, then g of x equal to f of x phi of x is again 0 because this f had support inside u tilde. Since support of f is contained in u tilde. So basically this g is identically 0. Therefore, g is identically 0. Now you act v on this, which implies v of g is 0. But v of g, now we can use Leibniz rule, the way we have written v of f times phi equal to f of p v of phi plus phi of p v of f. Well, f of p is 1, so this is just v of phi, and phi of p is 0 because p is inside u. So we get v of phi is 0, which is what we wanted. So let me continue this next time. So we'll stop here and I'll resume this argument in my next lecture. Thank you.